Hello, and welcome to this course on entanglement measures in 1+1 dimensional quantum field theory. My name is Olalla Castro Alvaredo. I'm a reader at City, University of London. You can see a couple of pictures of our place up there on the screen, and also some pictures of London for those of you that don't live in the capital. And in particular, one I like of the town hall that you see on the right, which actually reminds us a little bit of the concept of entanglement. So my talk is going to be divided into 4 parts. It's going to be, well, hopefully just 1 hour and a half. So I have to go rather quickly through a lot of material, but hopefully it will still be useful for those of you that perhaps don't know so much about these kinds of problems. So in the first part, very briefly, I will talk about some measures of entanglement so that at least we know what kind of thing we are computing. In the second part, I'm going to introduce an approach which I have helped pioneers a few years ago, in 2007, which is the use of branch point twist fields in the computation of partition functions and also measures of entanglement in 1+1 dimensional QFT. From there, we're going to move on to some more technical part of this course, which is about how to actually compute correlation functions of these fields using form factors as building blocks. And finally, I'm going to discuss one application of these techniques in some detail, in the form of a very detailed calculation that I will show you on the slides, but hopefully with enough detail that you would be able to reproduce it and understand the gist of it, and then apply it to some similar problems I'm going to give you at the end. So let's get cracking, and let's start with measures of entanglement. So how do we measure entanglement? This is part 1. So let's start from the beginning. So you all know what entanglement is, I think. So a quantum system is an entangled state if performing a localized measurement in a space and time may instantaneously affect local measurements far away. And this is typically exemplified by certain examples. For example, a Bell state, such as this one here. So probably all of you looking at that state know that this is a state that is maximally entangled for 2 spins. And what it means is that if you were to measure the state of the first spin in this particular state, you would immediately know what is the value of the second one, because they are always opposite from each other and they have 2 possible values. So in this case, knowing information about one part of the system gives us all the information about the other part of the system, at least in terms of the value of spin. It means that these 2 spins are maximally entangled. What is special about this is that Bell's inequalities tell us that this cannot be due to local variables, so that this is a genuine quantum effect. And by now we have quite a lot of evidence of this, in particular through Alain Aspect experiments from the 80s. So a situation that looks sort of similar to this would be a state such as this one here. And however, it's a completely different situation. It's sort of the reverse situation, the situation when there is no entanglement at all. And there is no entanglement at all in this case because the spins of these 2 spins now are completely coupled from each other. So if you were to measure the spin of the first particle, let's say the red spin, and you got some value, you would still know absolutely nothing about the spin of the second particle. So all possible states are equally probable. And so this is what we call a factorizable state. Now, this is all very simple when you just have 2 spins. You can compute everything very explicitly. But the question that comes to mind is what happens in many-body quantum systems? What happens if you have very many spins? And what happens actually is something very similar to what I just described. So instead of thinking about 2 spins, you might now think about a bipartition of your system. So you're going to divide your system of spins, your spin chain, if you wish, into 2 parts, A and B. And you're going to look at the state that describes the system, the whole system, whether it factorizes or doesn't. And let's think about about pure state. So it doesn't have to be a pure state to start with. It could be a thermal ensemble, for example. But in these lectures, I'm going to focus on pure states because they're already complicated enough. So if I have a pure state, and this can be factorized, as in the leftmost picture, then we're going to have, again, like the situation in the last example of the previous slide. So we have factorizable state, no entanglement between A and B. Whereas on the right, we have an example where those spins are talking to each other in the various regions, represented by the links on the picture. And in that case, the state doesn't factorize. And what that means is that if you try to sort of trace out the degrees of freedom of subsystem B, then the density matrix that you would get for what is left would look like the density matrix of a mixed state, purely because you have forgotten the environment. So I'm getting a little bit ahead in here, but let's say that this is the general idea. We still have to ask, mathematically speaking, what provides a good measure of entanglement? So the intuition is there, but how can we define mathematical functions that would differentiate between the state on the right and the state on the left? A good review of that is the one I quote here by Plenio and Virmani. So this is very nice because they talk about all sorts of measures of entanglement, which I won't discuss here. And they talk about their particular properties and why they are good at measuring the entanglement of certain kinds of states. Roughly speaking, however, if you want to find a measure of entanglement, it has to have some general features of interest, or desirable features. The first one, and this is actually something that comes very much from the area of quantum information, this kind of language, is that entanglement should be a monotone, so a monotonic function that doesn't increase under LOCC. So LOCC in quantum information means local operations and classical communications. And so what is a local operation? Well, this kind of language comes very much from the sort of Alice and Bob experiment. So Alice and Bob, they both own some qubit or some part of some state. They can perform a local operation on that state, for example. And the classical communication part might be that they communicate with each other by phone, let's say. It's a little bit difficult to translate that into the kind of problems we're talking about here, many-body quantum systems. But at least the idea that entanglement should be monotonic, so it should sort of grow if the state is more entangled. So if A and B are kind of more linked to each other, entanglement should grow. That is at least intuitively correct. It should be invariant under unitary transformations. So it shouldn't depend on how we describe those states, as long as they are related in this way. And we would like it to be zero for separable states. So that would be the sort of factorizable, separable or factorizable states we were talking about earlier. And then there is a last feature, which is usually, in brackets, it should be non-zero if the state is non-separable. So you might say that why we write the brackets there. So I guess you would expect that if there is entanglement, the entanglement measure should not give zero. However, interestingly, there are entanglement measures that can still give zero, even if the state is not purely factorized. And this is because in the context of quantum information, there is actually a concept of distillable and non-distillable entanglement. So there are some kinds of entanglement that somehow can be successfully put to use in some contexts, whereas others can't. So this is a kind of very subtle difference. For the measures that we're going to discuss here, you can remove the usually. So they are zero for separable states, they are non-zero if the states are non-separable. So these are desirable properties, and then on top of those, depending on which measure you like to use, there are other conditions that you can put. And if you want to know more, I again recommend that review up there. So some very common measures of entanglement that satisfy these properties are the bipartite entanglement entropy, also called von Neumann entropy. So this is the quantum generalization of Shannon's entropy. And then we have generalizations of these, which are called Renyi entropies. I'll define those in a minute. And then there are other measures such as logarithmic negativity, which are quite different. So actually this logarithmic negativity is one measure for which this usually actually applies in 0.4. So it can be zero actually, even if there is still some kind of entanglement present. And these are all good measures according to these properties. So I don't have a lot of time today to discuss a lot of this, so I'm going to focus just on the entanglement entropy. So Renyi and von Neumann, this is what's going to feature for the rest of the course. If you want to know more about logarithmic negativity, I could also provide some references. You can ask me. So I'll focus on the first two. So let me give some more precise definitions. So in this context, it's often quite useful to start with a spin chain, with a set of spins, simply because when we talk about entanglement, we are talking about locality very strongly. So we are talking about a part of the system localized in space and how entangled it is with respect to another part of the system localized in space. And a very easy way to visualize this kind of localization in space is to have actually spins sitting in places. So having a quantum spin chain. So this is an easier way to visualize these definitions than going to quantum field theory, which is what I actually normally do. So in the next slide, we will jump to QFT. So we'll take the scaling limit of this. But for now, let us think of a quantum spin chain that we have divided into two parts. So let's start with a simple bipartition. So we have part A and its complement, and we can imagine this same chain to be very long and to be connected at the end. So we could have periodic boundary conditions. This will not matter once we make the chain infinitely long, which is what we do in QFT. So suppose we have this configuration and we want to ask the question, what is the entanglement of A with respect to A bar, with respect to the rest? There are some useful definitions to this. And the most basic definition is the reduced density matrix, this rho A that you see in there. So this reduced density matrix depends on the state of the whole chain. And let's imagine that is a pure state phi. It doesn't necessarily have to be the ground state. It could be an excited state, of course. But later on, we're going to focus on ground state, and that phi would become a 0. So it could also be a mixed state, of course. You could have a thermal ensemble or something else. But as I said, it is already interesting when we have a pure state. So let's focus on that. Now, when we have a pure state, if we take the trace over the degrees of freedom of the complement of A, we get a reduced density matrix, which actually looks like the density matrix of a mixed system, simply because we traced out some degrees of freedom. And this curly A is the Hilbert space of the chain, and A's degrees of freedom live in that Hilbert space. So in terms of this reduced density matrix, we can define the entanglement entropy. So the von Neumann entropy, which is that function there, is a function of the length of subsystem A, L, and it depends on the density matrix in that way, through a trace, logarithm, etc. There are other measures, for example, Renyi entropies, I also mentioned earlier. So Renyi entropies depend also on the trace of this reduced density matrix, but now it is raised to some index, raised to some power. So sometimes people call this the nth Renyi entropy. Okay, so they are labeled by a number, which in subsequent slides, it would most likely be an integer. And actually, this is something we're going to be discussing. So what kind of number n can we put in there? So these Renyi entropies form a family of entropies, which have some very nice mathematical properties, but they also have one especially nice property, which is that if you take the limit n to 1, what you get is the entanglement entropy. So if you know all the Renyi entropies, you can get from them the entanglement entropy, okay? So computing then gives you the entanglement entropy in the end as well. It will turn out, because of the approach we're going to use later, that these Renyi entropies actually are, for us, more natural quantities to compute and more easy quantities to compute than the entanglement entropy. So I'm going to be focusing on this quite a lot in the remainder of this course. Okay, so these are the basic definitions. Now, the question is, given that these Renyi entropies somehow are a basis for computing the von Neumann entropy as well, we can try and compute them, and the basic quantity we need to compute them is this trace of rho to the n. So can we devise an interpretation for this quantity and a systematic way of computing it? So this is what we try to answer in the next page. And in the next page, not only we try to answer that, but we make the leap to quantum field theory. So let's imagine that now this quantum spin chain, we have taken the scaling limit. So we're looking at it from very far away, and we don't see the individual spins. We now see a field theoretical description of the chain with local fields. So how can we define this trace in that context? Well, people have looked at this problem in the past, so this is not a new question. And by various interpretations in various ways, people realize that this trace of rho to the n, if n is an integer, can be interpreted as a partition function. Okay, so this is the first place where we introduce a restriction on this number n. Okay, and where does this interpretation come from? Well, I cannot go into all the details, they're a little bit technical, and you can look at them in those papers, but the rough idea is the following. So if you have this trace of rho to the n, what is this rho? So this rho is the reduced density matrix. It is a matrix. And if we are in quantum field theory, this is a matrix whose matrix elements will depend on states on this quantum field theory. They will depend on the states on subsystem A, because for the rest of the system, we already took the trace. So we have kind of zipped that remaining part of the system. Now, rho A takes values, or its matrix elements rather, they take values in a space-time, so in the complex plane, which we can visualize as a sheet like the one in the picture. So we have this sheet, we have this region, which is region A in a space, and on either side of this region, if you wish, you can imagine having these two states, phi and psi. Now, when we take the trace of rho to the end, we are multiplying many of these matrix elements together, and they are connected. They are connected because it's a product, and they're also connected at the beginning and at the end because there is a trace. So the final state and the initial state are the same. Now, this object can be interpreted as a partition function properly normalized. So it's partition function set n divided set 1 to the n. We normalize it like this just to make sure that when n goes to 1, this becomes 1. And so what is the effect of constructing this trace of rho to the n? Well, if we see each matrix elements as this sheet of the complex plane, having many of these matrix elements put together could be visualized as a Riemann surface such as this. So in this Riemann surface that has n sheets, because we're doing a power n, these different copies of the complex plane have been connected to each other, and those connections reflect the connections of those states in the product up here. And at the end, because there is a trace, they are actually cyclically connected. So the first sheet is connected to the nth sheet. Now, this can be made more precise. So we can also see that in terms of a partition function defined in this way, okay, in the more standard ways. And in this case, what this means is that we now have a measure in here which takes values on this Riemann surface, on this Riemann manifold. Okay, and we have a Lagrangian here, which is the Lagrangian of whatever theory we're trying to compute the entanglement of. So in this picture, the sheets in the Riemann surface are connected to the product in the trace, and the connectivity of the sheets are connected to the notion of the trace that we are taking when we compute trace of rho to the end. Okay, so this is a very quick explanation of how this trace of rho to the end can be connected to partition functions in multi-sheeted Riemann surfaces. Now, in this case, we have a single branch cut because we decided to compute entanglement of a single connected region. But if we wanted to compute entanglement of these connected regions, we're going to have more complicated Riemann surfaces. So this is something I won't come to, but you can easily imagine. And you also have two branch points, of course, at the beginning and at the end of this branch cut. So, okay, this is the interpretation. Now, in this interpretation, as we said at the beginning, the fact that n is integer is quite crucial because it's the number of sheets on the Riemann surface. So this kind of poses a problem because, well, if we want to compute the von Neumann entropy, imagine that you want to do that, you have to take the limit n to 1 of essentially these Renyi entropies. Or if you want to use L'Hopital's rule, it means you have to actually do the derivative of this trace of rho to the n. And in order to do this derivative analytically, it means that you have to analytically continue this trace of rho to the n to values of n that are non-integers, that are actually real and bigger than 1. And that is a problem that from a mathematical point of view is not fully resolved. I call this the analytic continuation problem. It is a problem that I'm going to explore in my application that I will discuss in part 4, how we actually deal with this problem and solve this problem. So everything we're going to compute from now on is going to be for n integer. So to take this limit, eventually we have to ask ourselves how we analytically continue all these functions. So we'll see that a little later. Note, however, that when people do numerics, this is not a problem. So if you're doing a numerical calculation on a spin chain, for instance, using the MRG, and you are actually computing the eigenvalues of this rho A matrix, of this reduced density matrix, then of course, once you have the eigenvalues, you can compute any powers thereof. So there isn't really an analytic continuation problem there. There's only an analytic continuation problem if you try to understand these measures analytically in quantum field theory. Then you have to ask those questions. So for this reason, it's often easier to compute Renyi entropies by most of the approaches people use in QFT than directly the entanglement entropy. Okay, so it's a kind of formal reason derived from this replica trick. Okay, And so what else? So before I go to the next section, perhaps it's worth reminding you or telling you about the reasons why we want to study measures like this. So what is the point of studying these functions, okay? This is a question that people used to ask me years ago. Why do we want to compute entanglement measures if actually we cannot really measure these quantities experimentally? Well, actually, this has changed a little bit in recent years. So some of these quantities can be measured. And we can discuss that when we meet in a few days. But the original motivation, in my field at least, so in the context of low-dimensional quantum field theory, the motivation originally came from the fact that entanglement growth is a key indicator of how effectively a quantum system can be simulated on a computer. So it is very well known, probably to many of you, that the entanglement grows logarithmically in conformal field theory, for example. So it grows very fast, which means that conformal field theories are hard to simulate in a computer, whereas gap systems are easier to simulate. So these sorts of ideas actually prompted a lot of research in the early days in these kind of problems. And a lot of that research was numerical, for example, in these two papers that I mentioned here. Another thing that is kind of a quite different kind of motivation, which comes more from my perspective and the perspective of people doing analytic computations, is that the manner in which the entanglement entropy grows and other measures as a function of system size allows us to identify and classify quantum critical points. Okay, so essentially the entanglement of conformal field theories behaves in a very particular way. And the same happens for gap phases, for gap systems. So the entanglement of massive QFT also behaves in a very particular way. And so that means that if we compute these quantities, we actually are able to learn things about the nature of the quantum system, quite fundamental things. In fact, the things that we can learn are often universal features. So entanglement measures display remarkably universal features. They depend on fundamental properties like central charge, mass spectrum, rather than microscopic details of the system. And finally, more recently, people have realized that the dynamics of entanglement, so how the entanglement depends on time, after the system has been brought out of equilibrium, after a quantum quench, tells us a lot about the out of equilibrium dynamics of the model and the properties of the model. So this is a more recent development that is also, is also received a lot of interest. So there are many reasons to study these measures, but these are just some of them. Okay, so once we have talked about these generic ideas, let me tell you about how branch point twist fields enter the game here. So what can they provide apart from what I described so far? So let me go back to the picture that we had at the beginning. So our complex plane, the matrix elements of the reduced density matrix, and so on. So this is something I showed you earlier, but now I'm going to give you a different picture. So we still have a trace of rho to the n, which is a partition function. But what we have realized eventually is that this partition function can also be written as a two-point function of two specific fields. And this field T is what I call a branch point twist field. T dagger is its conjugate. And these fields are acting on a state phi, which is the state of the quantum system. And phi n means that this is the state not of the quantum system we started with, but of a replica version of that system, which consists of n non-interacting copies of the theory. So in this picture, what is happening is that we still have this Riemann manifold, but rather than trying to compute the partition function on this complicated geometry, we kind of are replacing that geometry by a correlation function. The price we pay is that the correlation function we are computing is a correlation function on a replica theory, because these n sheets somehow they match with n copies of the quantum theory we're looking at, non-interacting, but still. And the way these copies are connected to each other is only through this twist field. So at each branch point of this Riemann surface, one of these fields is sitting. And what these fields are doing is to implement the cyclic permutation symmetry of all these copies, of all these sheets. So in this picture, the sheets on the Riemann surface are equivalent to the replicas of the QFT, the copies of the model we consider. And the connectivity of these sheets is now implemented by this branch point twist field, in particular by its locality properties with respect to other fields in this n-copy model. Okay, so we have gone from a partition function now to a correlation function. So the name, this name branch point twist fields was introduced in our paper, in that paper. And in there, actually, we call the field that I call here T dagger, we call it T tilde. So I tell you in case you look at the paper. So T is a local field in this replica theory, in the n-copy theory. So with respect to the Lagrangian of this copy theory, but it's non-local with respect to other fields in the theory. And it is that non-locality that reproduces the structure of this Riemann surface here. So if you are not so familiar with the twist fields in general, let me tell you a little recap about what they are. So the branch point twist field is a quite interesting field associated to a symmetry, but twist fields in general are a very old idea in quantum field theory. So let me tell you a little bit more precisely what they are with a simpler example. So whenever there is an internal symmetry in QFT, there generally is a field associated with that symmetry, a symmetry field. This is very easy, for example, in the Icing model. So the conformal field theoretical version of this model consists of three primary fields: identity, energy, and a spin field. But in this theory also, it can be seen a slightly different way. We can see this theory also as possessing a fermionic field, phi. And if we perturb it, if we do a massive perturbation, we also have this Majorana fermion present in the theory. Now, the interesting thing is that not all these fields, 1, epsilon, and sigma, they are not all local with respect to this Majorana fermion. So with respect to phi, the theory actually divides into two sectors. So Neveu, Schwarz, and Ramon, that probably you are familiar with. So there is a C2 symmetry. Fields that are local with respect to the fermion are the identity, the energy, and mu, which is the C2 counterpart of sigma. But there are also fields that are semi-local, like the spin field sigma or order field. Okay, this is discussed, for example, in that paper of Yurov and Samologikov. And so what does it mean is semi-local? Well, as a picture, if you wish, you can think that what happens is that if you take a fermion phi and you take it around this field sigma, it comes on the other side picking up a phase. In this case, it picks up a minus sign associated with this C2 symmetry. Now, in order to describe this mathematically, what we tend to do is we tend to associate twist fields with a branch cut in a space-time. So a twist field, like sigma, sits at the branch point that initiates a branch cut in space-time, so that when you exchange sigma with another field that is non-local with respect to it, this is akin to going through this branch cut, and in this case, picking up a phase, okay? A more precise way to write that is to say that in general, we have two fields, a fundamental field of the theory and a twist field, phi in this example. And if we exchange them, depending on the order in which this exchange happens in space-time, if we don't cross the branch cut, nothing happens. But if we cross the branch cut, we pick up a factor, a phase. Yurov and Samologikov were the first to give a name to this. They call it an index of semilocality, I think. And in this example of the spin field, that would be simply -1, okay? So this is a basic example of a twist field, all right? So if there is a symmetry, there is a twist field. Now, when you have an n-copy version of the model, like we are talking about here, you have actually a lot of symmetry. You have permutation symmetry of all these copies. And so you have many twist fields related to those symmetries. But there is a specific one that plays a role in entanglement, and it's the twist field associated to cyclic permutation symmetry, which connects to the structure of the Riemann surface that we saw earlier. So in terms of this definition, our branch point twist field satisfies some exchange relations such as this. So if you have a field in your original QFT that was local in that QFT, when you replicate the QFT, you now have n copies of this field, which carry an index I from 1 to n. And because of cyclic permutation symmetry, when you arrive at n, kind of +1 becomes 1 again, and so on. So if you have two branch point twist fields like T and T dagger earlier, these fields satisfy exchange relations with a local field of the QFT. And these are similar to the ones I wrote for sigma, but slightly more complicated. What now happens is that when a local field goes around the twist field, if it crosses the branch cut, like in the first equation, it actually goes to the copy above, because that's what the twist field does. That's the symmetry it implements. It's kind of taking us from one copy to the next, and so on. And so going around the twist field is changing index I to I+1. If the field is T dagger, however, this is the opposite twist field, so implementing the opposite symmetry, the inverse symmetry, is the one that takes us down along the copies. And so if we go around T dagger, we change index from I to I-1. Okay? So these are the fundamental equations that define these branch point twist fields, and they're at the basis of the whole program that we have developed to use them in the context of entanglement. If you want to visualize this as a picture, it's a little bit like the picture before. So if we take a local field in copy I around the twist field, it emerges the other side on copy I+1. Okay? So, so this is the characterization of twist fields as symmetry fields. Now, having said this, many of you will be familiar with the fact that in the earlier work of Calabrese and Cardy, there is also a notion that entanglement is connected to correlation functions of some fields. So for that reason, I think it is useful to have a little bit of history of what these fields are and who found them first and where were they defined. So the answer to this is actually relatively complicated. In essence, depending on your point of view, you could think of these fields as appearing first in our work, on Calabrese's Cardy work, or even in much earlier works from the 90s, which is actually the more correct answer to this question. So the first time people talked about these kinds of twist fields, symmetry fields associated to set and symmetry, in orbifolded CFT, this happened in the 80s and 90s when people were particularly interested in orbifold conformal field theory, actually motivated by studies in string theory. And in those papers, some of those papers I cite in there, people studied these fields, identified the presence of these symmetry fields, and computed their conformal dimension, for instance. They found that their dimension was this value here. So it depends on the central charge, and it depends on the copy number, n. So this was found very early on and much, much earlier, much before anybody thought about these fields being useful in the context of entanglement. Then in 2004, Calabrese and Cardy wrote a very famous paper that is very much cited about entanglement entropy in the context of CFT. And they identified a field, they call it phi, of a dimension similar to this, but not quite the same. So their dimension was delta divided by n. And they interpreted this field as a field associated to conical singularities in the complex plane. So they didn't talk about symmetries and they didn't talk about replicas, but they talk about the Riemann surface, and they said, well, in each branch point, which is a conical singularity, there should be a field phi and its conjugate sitting. And entanglement measures should be correlation functions of that field. However, as I just said, the field has a different dimension from this field we're talking about here. And so the formulas that they get for the entanglement entropy, they are also a little bit different. So it's not exactly the same field. It's not the branch point twist field as defined in the previous slide. Now, the branch point twist field as defined in the previous slide appeared first in this paper by Cardy, myself, and Benjamin Doyon a little bit later. And in there is where we thought of these fields as symmetry fields. So that's where this symmetry field definition was given, and this connection to replica quantum field theory. So in a way, these three sets of references, they all made a contribution to the history of twist fields, and the early appearance of these fields is really in the 80s and 90s in the context of orbifolds. So, okay, so once we have this, well, what can we do? So the first thing is that if you get the pictorial idea of what these twist fields are doing, then it is not too complicated to imagine how you would then compute the entanglement entropy or the Renyi entropies of multiple disconnected regions. So suppose that you have a one-dimensional theory on the line, and you have all these regions, A1, A2, A3, and so on. You want to compute entanglement of the union of all these regions with respect to the rest of the system. So the general statement is that the Renyi entropy of that system would be related to a 2k point function, which would contain k twist fields and k anti-twist fields, and they will be sitting at the beginning and at the end of each of these regions. Okay, so essentially each boundary point in a space corresponds to a field. And so the more boundary points you have, the more complicated the correlation function you have to compute will be. But in general, you will have a formula such as this. Now in this formula, there is this epsilon here, and this is really a totally optional thing. It's a particular way in which we like to write these measures. It's just to have a space scale in there. So this is a non-universal UV cutoff. So if you're doing numerical simulations, that would be proportional to the lattice spacing in your quantum spin chain. Okay, so it's just a scale that gives you a non-universal constant that you can add to your entanglement measures. So you can either write it here like this, or you can write without epsilon, and then you write plus constant, and that constant is non-universal. So this is an optional way to write things. Now, with these definitions, the last thing I want to explain to you is how you can recover results that you probably have seen before using these twist fields. So one famous result, probably the most famous result, is the logarithmic growth of entanglement entropy in conformal field theory. And this is a consequence, a very simple consequence of this definition. So if you have a 2-point function in CFT, it scales in a very particular way with the dimension of these fields. So if you use that result, you immediately get this kind of result for the Renyi entropies. And if you set n equals 1 in there, you get the standard formula for the entanglement entropy of one interval in conformal field theory. And you see here that this epsilon, actually one way to define it is as a parameter such that if you write your entanglement entropy like this, there are no longer constant corrections to it. Okay, so it kind of puts together all the constant non-universal corrections to that quantity. And so logarithmic growth of entanglement follows from power law scaling of 2-point functions in CFT. And by the way, here we are always talking about the ground state in the replica theory, so 0n. So this is probably the most famous result, okay, that many people find in the paper of Calabrese and Cardy, but also had been obtained earlier by Hornsey, Larson, and Wilczek in the 90s, also using CFT arguments. Another result that you might be familiar with, and actually is particularly well known, I think, in the context of string theory, is that if you have two disconnected regions, for instance, or many, if you want, then the entanglement entropy, so the von Neumann entropy, is going to have a behavior that is quite similar to the one above. So it's also growing logarithmically with the size of the regions, but now because you have two regions, there are different length scales that enter the formula. And so you get logarithms of different distances between all these points. Actually, here I made a mistake. So this x2, x3 should be y2. So this would be x1, y1, x2, y2, okay, as in the correlation function here. So this is a typo, sorry about that. So, so you get a part which shows again logarithmic growth with length scale. And this is a formula that actually appears also in that paper of Calabrese and Cardy. It was a very celebrated formula. And in that paper, it was claimed that this formula was generic actually for many disconnected regions and for all conformal field theory. But later on, it was realized that this wasn't quite true. It was realized that actually, if you have a generic conformal field theory, you're going to have a correction to this, which would depend on some function of the cross ratio, because this is a 4-point function in this case. And that function is model dependent. It can be very complicated. So in other words, this function is only not there if the theory you're looking at is a free theory. Okay, for example, a free fermion or a free boson, I guess. So it's not completely generic, but it's still an interesting observation that you still have this logarithmic growth with the length of the system, of different length scales in the system. So these are two famous results in the context of CFT. In the context of massive quantum field theory, which is my area of specialty, there are also some very famous results. So I call these gapped systems. So in quantum field theory, we have a mass scale, which means in a discrete version of the theory that we have a gap. So we have a correlation length that is not infinite. And we generally have a mass scale, which you can think of as being the inverse correlation length in the system. So in gap systems, what people have observed is that if you have a system with a finite correlation length and you look at the entanglement of a very large region, that entanglement saturates. It becomes a constant that depends on the correlation length, but not on the length of the system anymore. And the reason why this happens is also very apparent when you write the entanglement entropy in terms of a two-point function of twist fields. So when you have a mass scale, correlation functions have a clustering property, meaning that if you bring the fields very far apart from each other, the correlation function is expected to factorize. And it is that factorization that makes the entanglement saturate. So if the two-point function saturates, what we have here now are expectation values of the fields, which are independent of the region size. And so the entanglement entropy does not depend on L anymore. This L shouldn't be there, really. It becomes a constant. It's a constant that depends on the mass scale, depends on this non-universal scale epsilon, and then there's some other constant U, and the definitions are down here. So these definitions follow from the standard scaling properties of expectation values in QFT. So the expectation value of twist fields should scale with the mass scale of the theory in these ways and with the dimension of the field. Then there will be some number, an, so pure number. And this un here is precisely depending on that pure number and on n. Okay, so these are the Renyi entropies. So this is saturation, and actually this is a result that was proven by Hastings as a theorem. Okay, so this is known to hold for gapped systems in complete generality. Another result that you might be a bit less familiar with is what the corrections to this result look like. So if you take the limit n to 1, you still have saturation. So the von Neumann entropy also saturates for finite correlation lengths and large systems. But if you look at a situation where the correlation length is small, but is still not so small compared to the length of the system, then what you have are corrections to the saturation result. And these corrections can be also computed with actually branch point twist field techniques. We computed them, and we showed that the entanglement entropy, so the von Neumann entropy, saturates and then acquires some corrections which are exponentially decaying and which depend on the mass spectrum of the QFT and on the length of the system. Okay, so we have some corrections when the length of the system and the correlation length are not so dissimilar from each other. Then there are corrections to saturation. And they describe the transition between the logarithmic behavior of CFT and the saturation behavior of massive QFT. So these corrections take a very universal form for all quantum field theory in 1+1 dimension. This is something we proved. And this is a calculation that I'm going to show you in part 4 of this course. So this is a very nice result because it's very simple and very generic, okay? So we will talk about this a little bit later again. So these are all results we can get from twist fields relatively easily. Now, just to show you that these results really can be also obtained when you do numerical simulations, I'm going to end this part by showing you some results for the Icing spin chain. So suppose that we have this Hamiltonian. This is a quantum spin chain called the Icing model. H is normally called the magnetic field. And this is a nice model to study because it can be mapped to free fermions, first of all. And it has two interesting scaling limits. The first one is if you set H to 1. So if you set H to 1 from the beginning and then take the scaling limit, this theory becomes a conformal field theory. So it flows to a critical point, which is the Icing conformal field theory with a central charge a half. If, on the other hand, you take H bigger than 1 and then take the scaling limit, what you get is a massive quantum field theory, which is the Icing field theory. Or if you wish, you can see that as a massive Majorana fermion. So that means that depending on the values of H that you choose, you can simulate or you can study the various kinds of behaviors I described just before in the previous 2 slides. And this is shown in these couple of pictures here. So you probably cannot read the labels very well, but doesn't matter so much. Just suffice to say that the picture on top, this is the entanglement entropy. Von Neumann entropy is as a function of system size. And in the legend, what we have is different values of H. And so the upper curve of all of them, this corresponds to H1, which is the critical theory. And what you see is a very clear logarithmic behavior there. In fact, you can fit that curve, and the fit that you get is this. So you immediately identify central charge equals a half, and then you have this number here, and you have the lattice spacing A, So having those two numbers, you can actually fix this non-universal scale epsilon that I had in my formulae earlier. So, so this is the pure CFT behavior. If you make h a little bit bigger than 1, not very much, you see that this logarithmic behavior starts to get suppressed. And eventually, if h is big enough, you see that you only have logarithmic behavior at the very beginning, and then you have saturation. And that saturation depends on h, because the correlation length depends on h. Then what you can do once in these cases is you can now look at these functions here and subtract the saturation value and see what is left. And if you do that, you get this kind of function here, which you can also fit, and you can fit very perfectly with this -1/8 K0 to ML. So this was this Bessel function correction I mentioned in the previous slide. So this can also be obtained numerically in a very precise way in this model, because it's a free model. So that's to show you that all these results are accessible numerically as well in numerical simulations. So now that we convince ourselves we can compute entanglement measures with twist fields, we can then ask, okay, so how do we compute these correlation functions of twist fields, not just for the 2-point function, but perhaps even for higher point functions, and particularly how we do that for massive quantum field theory. So in CFT, there are certain techniques that are accessible. For example, we can use conformal mapping. And this is how originally the entanglement of one region was computing, by mapping this Riemann surface back to the complex plane with two conical singularities. But if you're in a massive quantum field theory, you cannot use conformal mapping. You don't have conformal invariance anymore. So you have to do something a little bit different. And what you do is you can use form factors of these twist fields in particular as building blocks of your correlation functions more generally. So this is a whole program in itself, and I'm going to give you a very summarized version of it in the next few minutes. Let me check the time. Okay. So I think we are doing okay. So let's start with a preliminary definition then. So I'm going to go through this relatively quickly. So if you are not so familiar with 1+1D QFT, there are some references that I have recommended with this course that you can look at. But roughly speaking, what we need are a description of the states, first of all. So in 1+1D QFT, now it is natural to write k-particle states in terms of rapidities rather than momenta. And this is because in one dimension, rapidities are a very nice parameterization, both of the energy of particles and the momenta of particles. So we can describe a state by the rapidities of the particles and by their quantum numbers, mu1 up to mu_k. And we can even create a basis of in states if we order these rapidities in a certain way. And that ordering tells us the order in which these particles are incoming. So, so this is the basic definition that we will use. Now, if we have a local field located at space-time 0, 0, we can define its form factor, its k-particle form factor in this way. So it is a function. It's a matrix element between that state I defined earlier and the ground state. And yeah, it depends on the quantum numbers of the particles and on their rapidities. Okay, so this is the sort of thing that we want to compute. Okay, and actually this heading here, entanglement entropy, shouldn't be there, should be form factor. So this is also a typo. I'll try to correct this when I give you copies of these slides. Sorry about that. So it should say form factor there, of course. So we also need the S matrix to compute things. So we'll look only at the diagonal case. So we're going to look only at theories where there is no backscattering. So that means that if a particle A and B interact, so if A scatters with B, the out product of that is still A and B, okay? So that excludes, for example, Sine-Gordon model, which is a model you probably will be familiar with, but I'll give you a hint later on how you might treat that model as well. So for now, let's look at diagonal theories where the S matrix only has two indices. And the S matrix is defined like this. So the two-body scattering matrix relates a state with a certain set of rapidities to another state where you have exchanged two rapidities. Okay, this is the only thing that you really need to know how the scattering matrix enters in all these calculations. So you know that in integrable models in particular, the whole scattering is described by the two-body scattering matrix. So giving this is enough. And this is what we're going to focus on, integrable models from now on. So in integrable models, we can compute correlation functions. And we can do that by expanding them in terms of these form factors. And the usual way we go about this is that we start with a two-point function like this of two fields. We construct this projection, this operator, which is a complete sum of a set of these states I just introduced with the correct normalizations and integrations. And then we insert this between these two operators, O1 and O2. Now, because the form factor, technically speaking, is defined with the operator sitting at 0, if an operator is sitting somewhere else, we would like to move it to 0. And this is not difficult. We just have to do a translation, okay? And that is going to give us a factor here, depending on the momenta and the positions of this momenta of the particles, the position of the operator. So we can also relate this to a form factor. Finally, there is also a notion of Hermitian conjugation. So when you insert this complete set of states, you get form factors and you get conjugate form factors. And so it's important to have a notion, to have this definition here. So for example, that means that when we compute the two-point function of TT dagger, what we will get in the expansion of the correlation function is modulus of form factor square of T. Okay, so this is because of this relation here. So once you have all of this, you can write the correlation function as something like this. Now, in this process, something has happened. So you see that in this exponential, only the energies appear. And this is because I have also carried out a weak rotation. So if you wish, you could either see this field as sitting at position 0 time minus IR. So that would give that sort of thing. Or you can see it as sitting at position R and then carrying out a weak rotation. A weak rotation is equivalent to shifting all rapidities by I pi half. Okay. Now, if these fields are spinless, one property the form factors will have is that they are invariant when we shift all rapidities. Okay, that's equivalent to a Lorentz boost. So that nothing will change. It's just the sinh becomes cosh, and this becomes then a decaying exponential. Now, this representation is quite good. And sorry again, the heading here is wrong. I think it's because I copied some slides on a different file. And so the names of these boxes, they were changed. So this should say correlation function. Okay, so I'll correct that as well. So, so what's important here is that this provides an expansion which is rapidly convergent for large distance. So this is a large distance expansion, which is something that people in integral models like quite a lot. It means that it gives a good description of the large distance behavior, and it's rapidly convergent, which generally means you don't need to sum many form factors here, you just need a very, very few, in fact. What is somehow a bit surprising is that it turns out that this expansion often works very well, even when MR is rather small. Okay, so it actually also gives a decent description of the short distance behavior, which, by the way, should be described by conformal field theory. This is the UV limit of an integrable model. So this provides a way to test features of the underlying conformal field theory. So if we can look at short distances, that means that we can connect this two-point function in massive QFT to its counterpart in conformal field theory and check that they match. So this is a common thing people do in my area. So since the entanglement measures depend on branch point twist field correlators, it means that we can use this kind of expansion to compute, for example, the entanglement entropy of a single interval. Okay, and this is what we're going to be doing in our application later on. So how do we compute these form factors then? That is the question. So computational form factors is an old problem in the context of integrable quantum field theory. It goes back to the 70s with some early work by Weist and then Karofsky and Weiss for the Sine-Gordon model. And it was very much developed later on, especially in the 90s by Smirnov, with lots of papers, especially about Sine-Gordon model as well. And what all these people realized is that particularly in integrable models, these form factors, similar to the scattering metrics, they're very heavily constrained. In fact, they're so constrained that you can write a set of equations, a Riemann-Hilbert problem that you can solve for the form factors of any local field in your QFT. And these equations are of two types. There are equations that tell you about monodromy. So that means periodicity properties of these form factors as functions of rapidity. And there are some equations called residue equations that tell you about the pole structure of these form factors. And if you combine them together, you can essentially solve for these form factors. So good places to learn more about this are the books of Smirnov and of Musardo. And if you talk about branch point twist fields, well, these form factor equations have to be changed slightly. This is what I'm going to be discussing in the next few minutes. And how they have to be changed, this is something we discussed in our paper as well. So we derived this new form factor program for these branch point twist fields. So the form factor program was old when we revised it, of course, as I just said. So what I'm going to do in the following, I'm going to motivate for you where these equations come from in terms of pictures. It's quite easy to see. I will tell you what they look like for a simple twist field, like the sigma field of the Icing model, where you just have an index of semilocality popping up when you go around the branch cut or you cross the branch cut. And then I will tell you how that changes for the branch point twist field. So, so this is the phase for this field sigma. And this symbol here, which you saw already in the picture at the beginning for part 3, this is the sort of representation I would use for the form factor. So we have these incoming particles from the in state. You have the local field there, O, and then you have possibly a branch cut coming from this operator, which is this red line. So let's look at these equations then. Watson's equations, monodromy equations. So the first of Watson's equations describes the effect of exchanging two particles, okay? And the second is also called crossing, and it describes the effect of taking a particle on a trip around the operator, okay? Which is equivalent to 2 pi I rapidity shift. So let's see what these equations look like. So if you have a standard local field or perhaps a simple twist field, the first equation looks like this, the first Watson equation. It just says that if you exchange two rapidities in the form factor, you just should pick up the scattering matrix. And this is easy to represent graphically and it makes a lot of sense. So if you exchange two particles, you are generating a scattering process, so you pick up a two-body scattering matrix. So that's pretty simple. The branch cut has no effect on that property. On the other hand, the crossing property involves this index of semilocality for simple twist fields. And what this property represents is this process. So it tells us that if we take a particle on a trip around the operator and it is forced to cross this branch cut. So when I say particle, I can say fundamental field creating this particle goes around operator or field O. It crosses this branch cut, so we pick up this W and we bring θ1 to the end. But we could also shift by 2 pi I, so we could have also θ1 coming here. So I think that makes sense. So this is so this represents the final outcome here. This represents the 2 pi I shift. So if we shift the rapidity by 2 pi I, one of the rapidities, we bring that particle to the end, so that rapidity to the end, and we possibly pick up a phase, we pick up a factor. So these are the Watson's equations for a simple twist field. For a completely local field, this W is not there at all, and that's the only difference. Now what happens for the twist field? Actually, it's not very different. So the first equation doesn't change at all for the twist field. So situation is the same. We get a scattering matrix. But the second equation changes a little bit, because if we cross the branch cut now, we don't just get a simple phase. What we get is that this particle that was traveling around the operator, if it was in certain copy, J is going to go to the next copy, J plus 1. So what we see here is the effect of something I didn't mention, which is that when we talk about twist fields, we're talking about replica theory. And when we talk about replica theory, these quantum numbers of the particles are really a double number, double index. So these quantum numbers are now the quantum number of the particle, the same it had from the beginning. So whatever the properties, the quantum properties of this particle, but then there's an additional index, which is the copy number. So each of these particles in the state, they live on a certain copy of the theory, which may not be the same for all of them. And so if we take this particle around the twist field, it can travel to the copy above. So we effectively get a different particle, a mu hat, which is on a different copy. Okay, so this is a slightly different equation. It's the new version of the crossing relation for twist fields. Okay, actually, if you keep using this equation, which is something we will see a bit later, you can achieve coming back to the same copy you started with. And when you have done that, what you will see is that this shift here, instead of being 2 pi I, is actually 2 pi I n. Okay, and intuitively that makes sense because in a way, in this replica theory, your physical sheet of the complex plane has gone from being from 0 to 2 pi to 0 to 2 pi I n, because you have these n copies. Okay, so these are Watson's equations. What about sort of residue equations? So actually, for standard form factors, there usually are two types of residue equations, so two types of poles. There are kinematic poles, which are a consequence of annihilation of particle with antiparticle. And there are bound state poles, which are a consequence of particles interacting and forming a bound state. I'm not going to discuss the bound state poles because they are not so important and they are not always present in all theories, but you can see those equations in our paper, for example. So if we look at kinematic poles, which are more standard ones, so these are the poles that occur if a particle and an antiparticle are present in the form factor with rapidities that differ by I pi, so with opposite momenta. And if that happens, essentially these particles annihilate, and the form factor that we started with becomes, its residue is related to a form factor with 2 particles less. So we get a relation between a k+2 particle form factor and a k particle form factor. And for standard fields or for simple twist fields, the relation looks like this. Okay, so we have antiparticle mu bar and particle mu. Rapidity is different by I pi. Form factor is proportional, residue is proportional to this form factor. And the pictorial representation of this is that this annihilation process can occur in two possible ways. Either the two particles just annihilate on the left, or instead the first or the second particle takes a trip, interacts with everyone else, crosses the branch cut, and then annihilates. And this is reflected by this product of S matrices and this phase, which is the consequence of crossing the branch cut. So this is what happens for standard fields. For a twist field, what happens is a little bit different again, because the consequences of crossing the branch cut are a bit different. So what happens there? Well, in fact, for the branch point twist field, what you have instead are two separate kinematic residue equations, because these two annihilation processes are quite separate. They don't relate to the same form factor. So the first process is, okay, we have particle and antiparticle in the same copy and they annihilate. So that's the first equation here. Okay, so that's what happens in this picture. But what we could have is also a particle and antiparticle in different copies, so mu bar and mu hat, and they annihilate because actually when this particle interacts with all others and then crosses the branch cut, after crossing the branch cut, it finds itself in the same copy as mu bar, and then they annihilate. Okay, so the starting point is different in both cases, and that's why the equations have to be separated. The nice thing about this is that actually these two equations, although they look different, if you use the Watson's equations that I discussed earlier, you can show that they're actually equivalent. Okay, so if you use Watson's equations to bring this mu hat particle to the same copy as the particle mu bar, the effect of that actually is to transform the second equation into the first. So they are not independent from each other, which means that when you solve these equations, it's enough to use the first one and you don't need to worry about the second one. So these are the basic equations. This one is particularly important because it gives you a recursive relation between lower particle form factors and higher particle form factors. And if you can solve it generically, you might be able to come up with a general formula for all K. That doesn't happen very often, and it hasn't been, for twist fields, actually, this is only known for free theories, but for other local fields, in some cases, people have managed to find close formulae with very nice mathematical structure. So apart from this, well, there are other constraints that one can use to constrain these form factors further. And many of these constraints have to do with their transformation properties when you change the thetas, and their asymptotics. So for example, one common very important property is what happens to the form factors under a Lorentz boost. So if you shift all the rapidities by some constant amount, this is the same as doing a Lorentz boost. And if your operator had spin S, the effect of that would be to generate a phase, which means that if your operator is spinless, the form factor should be invariant under this transformation. And this is what happens to the twist field. So in other words, the form factors of the twist field can only depend on the difference of rapidities. They don't change if you shift rapidities. Another property that's quite useful is a constraint on how these form factors, how much these form factors can diverge if you make a rapidity very large. So this is a property that was studied by Delfino and Musardo in the 90s, and they gave an argument, it's not a proof, but they gave a quite good argument as to why a form factor of some local field cannot diverge faster than the conformal dimension of that field. And the reason they gave for this is that if this is not true, then the form factor expansion of the two-point function of this field that I wrote earlier would not be convergent. So this is a condition that can be helpful when you're trying to narrow down the possible solutions for a particular operator. Okay, and this is useful because, I mean, in everything I have discussed, I always talk about some local field abstractly, but in a QFT there are many fields. So the question is, if I solve the form factor equations, how many solutions am I expected to find? And how do I match those solutions to a particular field? So the operator identification, this is a difficult problem. There are other constraints one can use, but I don't want to discuss them here because it would be a bit too long. So let us just consider only this, okay, and the equations. So with these constraints and with the equations, we can now try and solve the equations. So how do we do that? Where do we start? So naturally, we want to start with the lower particle form factors. That's the standard approach. 0 particles is the BEF, is the backing expectation value. So this is just a normalization constant. So we can have 1 particle, 2 particles. In many theories, because of symmetry, 1 particle form factors might be 0. For example, if there is C2 symmetry, that's a frequent thing that happens. For example, in the Icing model, the form factors of twist field, for odd particle numbers, they are all 0. Also for free bosons, in fact. It's not always the case, but it's frequent. So something that people tend to focus on is looking at the 2 particle form factor, which is the first non-trivial form factor, the first form factor depending on rapidity that you have if your field is spinless. Because if your field is spinless, actually the 1 particle form factor is a constant, just like the BEF. So what do we need to take into account? Well, we have to remember that in the theory that we're working with, the two-body scattering matrix carries 2 indices, and each of these indices carries 2 indices as well, the particle type and the copy number. And because copies are not interacting with each other, that means that the S matrix has this structure. So if 2 particles are in different copies, the S matrix is 1, and if they are not, the S matrix is whatever the scattering matrix was in the original theory. So this is something we need to consider when we solve form factor equations, because the S matrix features directly in Watson's equations. And the usual starting point is to find a so-called minimal solution to the 2 particle form factor equations. So those equations, they can be written like this. This is a little bit different from what we saw, but what they reflect is the following, that the form factor depends on rapidity differences. So for 2 particles depends on a single variable, theta. If you exchange the rapidities, you change the sign of theta and you pick up an S matrix. This is the first Watson equation. This equation here is actually a combination of crossing and Watson's equation. So it's easy to prove. You can try and do that for yourselves as an exercise. But if you successively use the 2 Watson's equations, you come to this relation here, relating form factor theta and form factor shifted by 2 pi I n. So you can try and collectively solve these 2 equations. I mean, and it turns out there is a systematic procedure to do this, at least for diagonal theories, which is very simple. It's based on the following idea, which is that if the S matrix you started with, so this SA1A2, admits an exponential representation, and this is actually always the case for scattering matrices of hyperbolic type, so which are products of hyperbolic functions, which is the case for all diagonal theories I can think of, Icing, Sinch-Gordon, etc. You can go to a representation of this type, and if you have that representation, then you can actually show that this function down here solves the equation for this minimal form factor. So solves the two Watson's equations automatically, okay? So this is something that is also works for the local fields when n is equal to 1, and it works for the twist field. So this gives us the minimal form factor. So what is minimal form factor? I mean, why is it minimal? Well, it's minimal because it solves Watson's equations, but generally doesn't have any poles. So it doesn't solve the kinematic residue equation. It just solves part of the problem. So the minimal form factor is not the whole form factor generally, but it is part of it. And then you have to multiply it by some function that gives you the correct pole structure. So how do you try and find that function? Well, if you want to find higher form factors, in fact, generally you're going to start with a building block, which is the product of all those minimal form factors, for the same reason, because such a product would satisfy Watson's equations automatically. And then on top of that, you need to put the pole structure. So in this presentation, I'm going to focus on two particles. So I'm not going to tell you what the generic k-particle form factor looks like, but it's not very hard to get this. It's quite similar in reasoning to what I'm going to tell you. So you need to find the correct poles, the correct pole structure. So for two particles living in the same copy, so forget about copy indices for now, a correct solution to that problem is this. So here you have your minimal form factor that we talked about. And here you have the poles, okay? So this gives you actually two poles, which are at I pi and at I pi times 2n minus 1. So the pole at I pi is the kinematic pole, and the other one is the corresponding pole that you get by crossing, okay, by the last equation. You can check that this satisfies all equations, and I think this is even an exercise on the exercise sheet. If it's not, you can also do it. It's quite, I mean, a good thing to do. So that gives you the most generic, I mean, not the most generic, but it gives you a solution to the two-particle form factor. And this is, well, this is all we're going to need for our applications later on. So we're going to stop here in terms of the solutions, but you can, from this, using kinematic residue equation, construct higher form factor solutions. And we have done this for quite a few theories in our work. So this has simple poles on the extended physical sheet, which is imaginary part of theta from 0 to 2 pi n. And what you can see as well is that the function that contains the poles in there is a function that is 2 pi n periodic, and which is invariant when you change theta to minus theta. So in other words, this is a function that is carefully chosen not to spoil Watson's equations, to satisfy Watson's equations automatically, sort of trivially. The constants that you see here, they are there to make sure that the residue equation is satisfied with the correct residue. So when you take theta to I pi, the residue is just this expectation value of the twist field, this t. So okay, so this is the solution. Now, what do you do with different copies? So I said here that this is for particles in the same copy, okay? But generally you have many copies, so you need all the form factors. Now, rather than solving for all possible choices of the copies, one can be a little bit more smart and realize that the form factors in different copies, they're all related to each other. And this is due to the properties of these twist fields again, okay? So there is quite a lot of equations that one can write that relate these two particle form factors for particles in different copies to form factors for particles on the same copy, for example, the first one. And also there are relations between the form factors of T and those of T dagger. So here I write a couple of relations that you can also, as an exercise, try and prove, or at least argue that they must hold. And they're all quite simple. So for example, this relation here follows from the idea that all copies are equivalent. All copies are identical. So there's really no difference between copies, which means that if you have particles in copy I and I plus k, well, that's the same as having particles in copy 1 and 1 plus k. So that means that if you have a generic form factor, you can always shift it to place at least one of the particles in copy 1 without loss of generality, okay? And when I say 1, I could say any other copy number, but 1 seems to be a simple choice. So once you have done that, then you have a form factor such as this. And it turns out that if you repeatedly use Watson's equations, you can always bring this form factor related to a form factor where both particles are now in the same copy, both are in copy 1. The price to pay is that theta is shifted by some multiple of 2 pi I, which depends on the copy number, okay? And this is true for j bigger than 1, of course. For j equals 1, well, we don't need to do anything. Okay, now, what about T and T dagger? Well, T and T dagger, they implement the opposite symmetries, which means that in terms of particle labels, somehow to go from T to T dagger is as if you took the particle label of each particle, so let's say I, and you replace I by m minus I. Okay, so in a way, the actions of T and T dagger are interchangeable if you relabel the sheets in the Riemann surface. So you call the sheet n, you exchange n with 1, n minus 1 with 2, and so on. So you reverse the whole definition. And so that means that there is, just by construction, just by definition, there is this relationship between form factors. And then once you have that, then you can use the 2 results above to also connect a form factor of T dagger with a form factor of T via a shift. Now, if you keep going more generally, you can show more completely generally that a form factor of K particles in potentially different copies is always related to a form factor of K particles in the same copy up to appropriate shifts and in a very particular order. Okay, so this only works if J1 is bigger J2 and bigger Jk. Okay, and theta J represents the shifted rapidity. Okay, so because of all these relations and others that one can write, we generally always work with form factors in a single copy, and then when we need other copies, we just exploit this formulae here. Okay, now a special feature that will play a role in what I'm going to tell you next is that the form factors of this twist field, they're all 0 when n goes to 1. I mean, and if you think about it, that makes sense, because when n goes to 1, we don't have copies anymore. And when that happens, we don't have symmetry either, and the twist field becomes the identity. Okay, and so all its form factors are 0, except the vacuum expectation value, which is 1. Okay, so this is a property that becomes very important when you compute the von Neumann entropy, because when you compute von Neumann entropy, you need to take a limit when n goes to 1. And because of this property, actually many things vanish. And this is one reason why in the end one can get pretty simple results after doing the analytic continuation carefully. Okay? So this is all I wanted to tell you about form factors, solving equations for form factors, and so on. This is quite a technical approach, and well, not all of you would be perhaps so interested in the details, but it is really a very powerful approach within integrable models, not just for twist fields, but for generic quantum fields. So in the last part of my talk, and let me check the time. Okay, I think I'm all right. So in the last part, that is not too long, I'm going to show you one application in some detail. There is an exercise, the last one on my exercise sheet, which is similar to what I'm going to describe here. So we'll give you an opportunity to try and see if you understood all the steps and can apply them to a slightly different problem. So the application that I want to discuss is again about this 2-point function of twist fields on the ground state. Which means computing the Renyi entropy of one integral in massive QFT. Okay, so if we wanted to compute this, what kind of things will be involved? Well, there's going to be a form factor expansion, which is going to involve sums over, well, 1 particle, 2 particle, n particle form factors. So the kind of sums that are going to feature, especially for 1 and 2 particle form factors, will be the ones I'm going to show you right now. So for 1 particle form factors, we're going to have a sum such as this. So these are 1 particle form factor particle mu, and we are summing over particle types and over copies. Okay. Now, because all copies are identical, and we only have 1 copy index, what we can do is just write n here and remove the sum over copies and put our particle in copy 1. Okay, so this is one of these common simplifications one can do. And then in the next step, we can perhaps just forget about the copy altogether. Okay, so we will get something like that. And that's why we always get a factor n in all these computations. If you have two particles, well, there's a little bit, there are a few more steps. Now you're going to have a sum over 4 indices, so the particle types and the 2 copy numbers. But we said earlier that you can always place one of these particles in copy 1 because all copies are equivalent. And again, you can do that at the price of getting a factor n out in this computation. What else? Well, we saw earlier in the previous slide, I think, that, or 2 slides ago, that this kind of form factor can be related to form factor in copy 1 by shifting the rapidities. And this is what I have done in this step. So I separated the term j = 1 from the rest, and they look like this. And then I can even do something more, which is very trivial. I just shift j by 1, and I end up with this kind of sum here and this term in here. Okay, so we still have the sum over particle types. Okay, so it looks relatively complicated. But if we look at a theory where there is, for instance, just one particle type, like the Icing model or Sinch-Gordon model, then those sums actually also go away, and this becomes relatively simple. So this is precisely the sort of situation we're going to discuss in the next 10 minutes or so. So let me go back to these exponential corrections. So this is a formula I showed you earlier. I told you that this was a result that we got from branch point twist fields. And it shows that the entanglement entropy of a region of length L saturates for L very large. But if L is intermediate, not so large compared to correlation length, it acquires corrections, which are exponentially decaying with the length of the system. And the corrections take a very specific form. They are Bessel functions involving the masses of the particles in the spectrum with a very precise coefficient, which is -1/8. Now, this result is valid for integrable quantum field theory, but it's also valid even beyond integrability. So it's really very, very general. So it's a result that we can also test numerically. Here we have 2 pictures. One of them we saw earlier. So if you look at the entanglement entropy of a gapped system and subtract the saturation value, what is left should be these exponential corrections. And they can be detected numerically. In Icing, they can be detected very precisely. But even in the Sine-Gordon model, so in the XXZ quantum spin chain, in a particular limit where we get Sine-Gordon, we can also find quite precisely these Bessel functions. And in fact, in the Sine-Gordon model, we get this result, a single Bessel function with coefficient -1/4, because there are 2 particles of the same mass, which are the lightest particles, so soliton and anti-soliton. So that means the entanglement entropy actually gives us information about the mass spectrum, at least the mass of the lightest particles, because for the heavier ones, well, this would be very, very, very small corrections that we have in here. So numerically, what we can aspire to find or detect usually are the lightest particles in the spectrum. So let's see how we get this result then. Let's look at the calculation. So we want to compute this 2-point function with this non-universal scale in there. And the entanglement entropy is by replica trig, is just going to be the derivative of this function. So the problem of having an integer is a problem that's going to come up a little later, but just let's ignore it for now. And let's look at this 2-point function. So we have all those terms. Vacuum expectation value, 1 particle form factor, 2 particle form factor, and others. Now, the vacuum expectation value, this is what is going to give us the saturation. So we have already discussed that. So we're not going to talk a lot about that term. And from now on, we're going to focus on a theory with a single particle. So we can get rid of all these sums over particle types. But if we have more than 1 particle, it's the same derivation, nothing much changes. So let's look at 1 particle form factor contribution. 1 particle form factors of spinless fields are constant, so we can take them out of that integral, and we just get this kind of Bessel function. Now, you would say, aha, this is the Bessel function, so that's a very easy thing to compute, but this is not the same Bessel function. You see, it doesn't have a 2 here, and it doesn't have a 1/8. Now, this Bessel function is there if the 1 particle form factor is not 0. And so it's going to give us the leading correction to saturation for the Renyi entropies. But if you take the limit n to 1, which is what you need for the von Neumann entropy, in that limit, the one particle form factor is 0, like all form factors should. Okay, remember, twist field becomes the identity. And so because the one particle form factor behaves in this way, when n goes to 1, this term is not going to be there. So this is not the leading correction to the von Neumann entropy. This is the leading correction to the Renyi entropies, provided these F1s are not 0. Okay, so the Renyi entropies are a little bit more messy and more complicated than the von Neumann entropy. So that is the one particle form factor contribution discussed. It's very simple. And because these form factors are analytic functions of n, the analytic continuation question doesn't really pop up yet in here. So let's look at the two particle form factor contribution. That's the interesting one. So we have seen this sum a little earlier, yeah? And here I'm writing it again. So what I've done really is I took out the term j equals 1 and I put it out here so I can start. Sorry, I took a term j equals 0 and subtracted it here and added it here. So we have a sum from 0 to n minus 1. That's a little trick, which makes the sum a bit nicer later. So these are the two particle form factor modulo square, okay, in copy 1. So 1, 1 means the same particle, same copy. So we have this term in here, and this term in here, again, is going to give a contribution to Renyi entropies. But when n goes to 1, all these form factors are 0, so that's not going to give a contribution to the von Neumann entropy. So these factors there, they don't really matter very much for what I'm going to say. So what we need really, what is non-trivial, is that sum. I mean, you would say that when n goes to 1, this sum should go to 0 as well. But remember, you don't just need to take the limit, you need to take a derivative. So how do you do a derivative with respect to n of a sum where the limit is also n? Okay, you cannot do that directly. You have to write this sum in a different way. And that is where kind of the key of the calculation is, and of the analytic continuation. So, okay, that is the sum that is left. And when you put it inside the integrals, in rapidity integrals, you have some integration like this, and you have this derivative and this limit to compute. You can perform one of the integrals, of course, that's very standard. The form factor only depends on theta, but here we also have beta. So when we integrate, we get this Bessel function. So this is the Bessel function that would eventually give us our result, the 1/8k0. So, okay. So how do we proceed from here? How do we deal with this derivative? So what we have to do is to get rid of that sum, okay? And one way to do that, and perhaps not the only one, but a standard way to do that, is to replace that sum by a contour integral, okay? So if you all have studied complex analysis, I guess. So this would be a sort of trick that you're probably familiar with. So if you cannot perform the sum, you can instead write a contour integral over a contour which contains as many poles as terms in the sum, and such that the residue of each of these poles gives us the terms in that sum precisely. Now, one way to do that is to use something that is sometimes called cotangent trig. So cotangent trig means that you replace that sum by a contour integral that contains a cotangent. And this cotangent has poles at all integer values of this variable z. Now, this variable z is the continuous version of the summation index of the j that we had in the previous sum. Okay, so z is now that variable, and we now have that contour integral with that function here. Okay, so that's good. So does this help in any way? Well, it does help in the sense that now n appears as a continuous variable. That is good. So we have some hope to compute the derivative. However, there is something that we have to take into account. So our integration contour, we're going to choose it like this. So it's going to be a big box, a big rectangle, or a rectangle of certain length, L. And this rectangle contains these poles on the real line corresponding to z equals, well, 1, 2, up to n minus 1. So these are the poles of the cotangent that we want to produce the sum. But then we have the contour itself, and then we have some extra poles, these blue crosses. And these extra poles, they're actually the kinematic poles of this form factor, because the form factor has these kinematic poles at I pi and I pi to n minus 1. And because there are two form factors, that gives 4 poles. And if you work them out, they are exactly at these points in here. Okay. Now, remember that the sum was from 0 to n-1 in the original formula. So if we want to contain the pole at 0, what we can do is to shift this rectangle a little bit towards the left, and we want to avoid the pole at n. Okay, so we're gonna imagine that we are doing that. In fact, including the pole at 0 or not doesn't really change the final result, but just for consistency with the sum that I wrote earlier. So this is the calculation we need to do, right? So we have to compute the contribution of the contour integration and the contribution of the blue poles, and from that evaluate our sum and eventually our derivative. Okay, so let's look at the integration over the contour. So the first thing is that if you look at the contributions of the horizontal segments of this contour, well, it turns out that you can argue that this function s decays exponentially when the imaginary part of z goes to plus or minus infinity. And that can be used as a reason to show that the horizontal segments should not contribute. Now, this comes out of nowhere, I mean, that condition. So I can only tell you that this is essentially equivalent to saying that these form factors, they go to 0 when theta goes to infinity. And this is a quite natural property for these two particle form factors that we are using here, okay? That doesn't tell you the deep reason. If you want a little bit more reason for that, you should ask me about it when we have the live session a little bit later. But let's say that this is a very natural condition for most theories, okay? Form factor going to 0 when theta goes to infinity. So that has the consequence that we also have these properties, and we can forget about the horizontal bits of the contour. Then we have the contribution from the vertical segments. So what does that look like? Well, there are two contributions, but it turns out that these form factors, they have some periodicity conditions, as you know. In fact, this is what we have used in here. So it turns out that if we shift these form factors, if we shift the variable z by n, that is related to the unshifted function. And this is why we can collect these two contributions from the vertical segments into a single integral. And it looks like this. So it has a sort of the S matrix in there. One thing that you can observe about this integral is that this is 0 for free theories. So if the S matrix is plus or minus 1, which would be the free boson or the free fermion, then that would be 0. Okay, so this is a simplification that happens for free theories. It's not the only one. However, even if the theory is not free, we have once more that now we have a function of n, a continuous function of n. We can take its derivative, and when we send n to 1, this is going to be 0. And I mean, one way to see this is that this s function contains two form factors. So when you differentiate, there will be always one of them at least that is going to 0 when n goes to 1. So actually, once more, this contribution will be irrelevant for the von Neumann entropy, but it will be there for the Renyi entropies. So we shouldn't forget it in that case. So since we are focusing on von Neumann, we can now say, okay, the contour itself gives no contribution. We managed to forget about horizontal segments, and we argue that the vertical segments also, they do not contribute. So what are we left with? Well, what is left now really are the poles in the complex plane, the blue crosses in my picture. So these were the kinematic poles. And the kinematic poles, they have residues, and the residues, they can be put together to give this function here. Okay, so the tang comes from the cotangent in the integral evaluated at those poles. And these form factors come from evaluating the residue because each term has a form factor square, essentially. So when you evaluate the residue, only one of these form factors is left. So we end up with this kind of function. Okay, now this function, I mean, it doesn't look so different from some functions we saw earlier. You could kind of say, okay, when n goes to 1, this goes to 0 as well. Everything is 0. Well, sort of, but it's a bit more subtle than that. So we are almost there. Let's see what happens. So we look at this function, and yeah, this is 0 when n is going to 1. But if you look at this function a little bit more closely, what you realize is that something very special happens if you send n to 1 and theta to 0 simultaneously. So although this is 0 when n goes to 1 in general, when theta is 0 before sending n to 1, then things change a little bit. This has to do, well, this can be explained in different ways. One way to explain it is that when n goes to 1, in fact, the two kinematic poles, they collide. So you actually have a double pole instead of a single pole. But one nice graphic way to see it is to actually evaluate the sum that we started with for θ equals 0. And this is a picture that comes from our original paper, 2008. And you can probably not see the details very well, but I can explain them to you. So if you look at this line, blue line here with all those dots, this is the result of the sum for different values of n at θ0. So this is just a function of n. This is for the Icing model. So this is S matrix -1, pre-theory. And if you evaluate this sum for the Icing model, it can be done actually analytically, explicitly. The result of this sum is exactly n divided by 2, is n half, okay? And this is the straight line that you see here. It's the function of n, f of n equals n half. Now, the interesting thing is that that function, when n goes to 1, is not 0, is a half, right? So on the one hand, we know that these functions here are all 0 when n is 1. But on the other hand, we see that the natural analytic continuation of this sum when n goes to 1 is a half. Now, this is something you see for Icing, but if you look at an interacting theory like Sinch-Gordon, which is the other line here, you realize that this also happens there. So if you look at Sinch-Gordon, and if you look here in the inset, you look at small values of n, so how it approaches n equals 1, you see that these dots, which are the the numerical values of the sum, when you approach 1, they approach a half again. Okay, so although the individual terms in the sum, they should go to 0 when n goes to 1, the natural analytic continuation is telling us that this function is going to 1/2. So something strange is happening around θ0. And the more precise way to express that is to realize that these form factors, when n is near 1 and θ is near 0, their leading behaviors, they look like this. And if you look at that, you see immediately that this is a representation of the delta function. So what you have is actually a function that goes like n-1, delta function of θ. So at θ equals, so there is almost no contribution to any of this, but there is a very crucial contribution, which is precisely at θ equals 0, and it is the delta function. Now, once you realize that, the rest is simple. Remember, there was an integral in θ, so that integral disappears. There was a Bessel function of 2ml cos θ ½ which becomes a Bessel function of 2ml. And what you get is this very, very simple result, okay, just from this observation. Now, the nice thing about this result is that it is very simple. It's very generic, so it doesn't matter what theory you were working with, whether it was free or interacting, how complicated the form factor was. In the end, the only thing that mattered actually was the kinematic pole structure of the form factor. And that structure is very generic. It's actually universal. It's not even unique for integrable models. It's also present in non-integral theories. And so that's why in this paper, Benjamin was able to show on more general grounds that this would be the leading correction, even if integrability is absent. Okay, so I hope this example gives you some idea of how you actually do sort of calculations with these techniques, and you can apply that to some of the exercises that I have proposed. And that this gives you also an idea of how this form factor technique is quite powerful and quite useful in computing measures of entanglement in 1+1 dimensions. And there are many new developments in this area still happening. And so the story of branch point twist fields is not finished. So watch this space. There will be more talks about this and more developments. But for now, I hope this was instructive and useful. And I hope you enjoyed the problems. And I hope to see you in the live session a little bit later this month. Okay, so we end here. See you.